Building energy usage is certainly a very significant portion of our total energy usage. And certainly better optimizing HVAC systems can make a significant dent in our energy usage, or better optimizing the design of buildings can make a significant impact. Within Differentiate, we're trying to develop 3 different engineering design capabilities. We're trying to develop better optimizers, we're trying to develop better evaluators, and we're trying to develop generative models that are capable of generating designs instantaneously. Julia is working specifically on the ability to model HVAC systems in buildings, effectively simulate buildings and their associated HVAC systems dynamically to try and make temperature, relative humidity projections, versus time as rapidly as possible, to enable optimization of the controls, to enable the optimization of the HVAC systems that keep people in buildings comfortable.
Our company is Julia Computing. It focuses on building products around the Julia language. Julia is used largely by mathematicians, engineers, and scientists because they love the fact that it's as easy as Python and as fast as C. We say that it solves the 2-language problem.
The Julia programming language is founded on the idea that an engineer does not have time to rewrite code, right? So you have slow languages like Python and R, which people use for prototyping, and you have fast languages like C or Fortran that people use to actually put code into production. But with the Julia programming language, we've combined the two. So everything that you build in the energy sector, be it an HVAC model or a new car, all of these have computing involved, because you want to make sure that the first time that you actually go and build the product, that very expensive step, you want to make sure that you do that right. And what we're doing with Julia Computing is we're accelerating computations so that way the full physical model with all of the physical details can be captured and ran quickly by an engineer. So that way when you finally get to the line to build it, you know that you're going to have something that works at the level that you expect it to. The machine learning techniques are trained over a search space. So for example, with HVAC systems, it would be like the refrigerant properties that one might be interested in designing for, or for designing new batteries, it could be the different catalytic properties. And what we can do is from different samples of the space of properties, we can then predict how the material would act at new properties without having to run the full simulation. We've seen it give a 570 times acceleration in HVAC modeling. We've seen it give a 340 times acceleration in circuit models. We've seen it give more than 100 times acceleration in quantitative systems pharmacology models. So all these kind of disparate domains in scientific modeling seem to get very similar results, and that result is Julia Sim can accelerate the simulation.
This is why the world is using Julia at large, especially engineers designing new energy systems, whether it's simulating wind farms, or designing a new turbine, or designing a new air conditioner, or designing a new material for a battery, or designing a new electric aircraft. Like, Julia pretty much is increasingly the language of choice for all of these engineers.
And so the tools like what Julia is developing will be critically important enablers to engineers as they design better buildings and better HVAC systems, learn how to control them more efficiently.
We'll be able to design everything around us to better suit the heat needs of every individual without requiring any more energy or without requiring any more resources, just by understanding the physics and the biochemistry at a much deeper level.